Okay, this is the exam 3 from MA161. This is from the fall 2018 semester. So let's get started. Question 1, just compute the limit. So we've got the limit as x approaches pi of a big fraction. So through all the limits that we've done so far, we know that the first thing we should do, especially with these big fraction limits, is just plug in the value that x approaches. And then based off of what comes out of that, we can determine our next steps. So let's go ahead and plug in pi for all these x's. So we're going to get sine of pi minus pi all over pi squared plus 4 pi squared minus 5 pi squared. On the top, this is going to be sine of 0, which is 0. And on the bottom, we're going to have pi squared plus 4 pi squared. So this is going to be 5 pi squared minus 5 pi squared. So on the bottom is also going to be 0. So cool, we have 0 over 0, which is an indeterminate form, which is just either 0 over 0 or infinity over infinity. And because of that, that means we can do L'Hopital's rule. So what L'Hopital's rule says is if you have an indeterminate form, like we have here, you can take the derivative of both the numerator and the denominator, and your limit won't change. And usually when you do this, the denominator will, after you take the derivative, it'll get rid of whatever property is making it divide by 0. So after we do this, the denominator will no longer equal 0 after we plug in pi, and we can just find our limit normally by calculating the output. So let's go ahead and take these derivatives. So on the top, let's see, we have derivative of sine of x minus pi. So derivative of sine, that is cosine. So we have cosine of x minus pi. And then we have to multiply by the derivative of the inside. We have to do chain rule. So derivative of x, that's just 1, and the derivative of minus pi is just 0 because it's a constant. So we just multiply all of this by 1, which doesn't do anything. So our derivative for the numerator is cosine of x minus pi. And then in the denominator, let's see, derivative of x squared is 2x. The derivative of 4 pi x is just 4 pi, so plus 4 pi. And then 5 pi squared, that's just a constant. There's no x term in it, so derivative of that is just going to be 0. So on the denominator, its derivative is just 2x plus 4 pi. So now let's see what happens when we plug in pi for x. So let's see, we'll get cosine of pi minus pi again. But fortunately, cosine of 0 is not 0, which is good. And then on denominator, we have 2 pi plus 4 pi. Cool, this isn't gonna, this looks like it's not going to be dividing by 0 anymore, and whatever answer we're going to get is going to be our answer. So in the numerator, cosine of 0, that is, that's 1. And then in the denominator, we have 2 pi plus 4 pi, which is 6 pi. Our answer is A. Question 2. This is another limit question, but it's not really a normal limit question. This question isn't really testing your limit finding abilities. Like, it's not asking you to calculate anything. It's just asking you if you remember what this specific limit looks like, if you've seen it before. And I don't know if it has an exact name, but what it is let's rewrite this in a little bit differently. Limit as x approaches 0 of 1 plus k times x, all raised to the 1 over x power. This just equals e to the k, where this k is a constant that you put in there. Now, in this case, our constant is -2, so our answer is going to be e to the -2 power, answer choice E. And for that reason, I don't really like this question just because it's, probing your memorization instead of asking you to, work through a problem. But I don't know. Sometimes the math department likes to do that. Question 3. We've got a related rates problem. So if each edge of a cube is increasing at a constant rate of 3 centimeters per second, how fast is the volume of the cube increasing when the length of each edge is 10 centimeters? Okay, so let's draw this out. That's always a good idea for related rates. So we've got a cube down here. There we go. Cubes have all of the sides are the same, so let's do S for all of the sides. And we need to find the rate at which the volume is increasing when the length of each edge is 10 centimeters. So first thing we do for related rates is determining what formula we need to use to solve this. That formula should relate a lot of these pieces of information together. Now, since we're given a lot of side lengths and we're asked to find the rate of volume, we can probably just use the regular volume formula, where it's the side length cubed. So V equals S cubed. Now our next step is taking its derivative. So derivative of V, that's just going to be dV over dt. And then the derivative of S cubed, that's going to be, if we do power rule, bring the 3 out front, it's going to be 3S squared, because we minus it by 2, and then times ds over dt. Cool, so we have this formula now. Now we just need to plug in the information that it gives us. So, excuse me. So we're trying to find the rate at which the volume is increasing. So we're trying to find dV over dt. So the problem should give us both S and ds over dt. And it looks like it does. So ds over dt, that's going to be 3 centimeters per second. That's the rate at which the edges are increasing. And then S, that's going to be 10 centimeters. That's the side length that the sides are at that instant when it's increasing at 3 centimeters per second. So let's go ahead and plug those in. dV over dt equals 3 times S, which is 10 centimeters, times ds over dt, which is 3 centimeters per second. Multiplying all these together, we get dV over dt equals 3 times 10 squared is 100, so 300. 300 times 3 is 900. Answer choice C. So restating this problem, at the moment when each edge is 10 centimeters, the volume of the cube is increasing at a rate of 900 cubic centimeters per second. Question 4. Using differentials, aka linear approximation, to estimate the square root of 9.1, the approximate value is what? All right, so this is a linear approximation question. The formula we use to solve that is f of x is approximately equal to f of a plus f prime of a times x minus a. So we have a few things we need to find before using this formula, though. Namely, we need to find x, we need to find a, we need to find f of x, and f prime of x. So we need to find all 4 of these before we can go ahead and use this equation. So our x, that is the weird decimal value that's inside of this equation. In this case, it's going to be 9.1. That's the weird decimal value. A, that's going to be a value that is very close to x, but would be much easier to calculate if we used that instead of x. Now, since we have a square root here, and since 9 is really close to 9.1, and 9 is way easier to take the square root of, let's make that our a. So a equals 9. Now, our f of x, that's just the original problem, but with an x instead of the 9.1. So that's just going to be the square root of x. And then our f prime of x, that's just f of x's derivative. So if f of x, that's just equal to x to the 1/2 power, that means f prime of x is 1/2 times x to the negative 1/2, which is just equal to 1 over 2 times the square root of x. So there we go. We have all 4 of those. Now we can go ahead and use this equation. So f of x is approximately equal to f of a, that's just going to be the square root of 9, plus f prime of a, that's going to be 1 over 2 times the square root of 9, times x, which is 9.1, minus a, which is 9. So there we go. Now we just have to simplify this. So let's see. Square root of 9, that's just 3. 1 over 2 times the square root of 9. So square root of 9 is 3. 2 times 3 is 6. So this is going to be plus 1/6. Plus 1/6. There we go. Now we've got 9.1 minus 9. That's going to be 0.1, which since we have, we're multiplying this by a fraction here, let's go ahead and turn 0.1 into a fraction. Let's make it 1/10, just so it's easier to calculate. So there we go. One more step. Let's see, 3 plus Actually, that was pretty stupid because the answer is probably going to be um, no, that was not stupid actually, because I think our answer is going to be D. So let's make everything in terms of fractions here. I think that was smart to keep it in fractions. I thought we were going to have to use decimals instead because some of these answer choices have decimals, but I think our answer is D, so which has a fraction. So let's keep things in fractions. So this is 3 plus 1/60th, which is just 3 and 1/60th. I guess they put it in that weird form that you haven't used in like 8 years. But anyways, the answer is D here. Question 5. You are the owner of a rectangular orchard adjacent to a straight river. You have 1,000 feet of fence that you want to use to enclose it. No fencing is required along the river. If x is the length of a side perpendicular to the river, and y is the length of the side parallel to the river, find the values of x and y that will maximize the enclosed area. Okay, let's draw this out. This is kind of a related rates problem, but just sort of a maximizing, minimizing cost and area type thing. So we've got our straight river down there with fishies in it. That's a terrible fish. There we go. That's our river, and then we have an adjacent fence that's built next to it. So we've got a fence that's right here, and we don't need to build a fence right here. I guess if there's like animals in the pen, they can't swim, so you don't need a fence built along the river. So our x is the length of a side perpendicular to the river, so that's these two fences right there. And then y is the length of the side parallel to the river, so that's the length right there. It's all a rectangle, so we've got right angles all around. And we're asked to find the values of x and y that will maximize the enclosed area. So we need to find x and y that make A as big as possible. Now, this exam I think is going to be the second to last exam that I record, or it's going to be the second to last in terms of like time. Like it's pretty late into the chronology on the exam archive. So at this point, I'm pretty sure you've already come across a question like this. So instead of doing all this work, I'm just going to show you the shortcut. So for every single one of these fence built along a straight river problems, y is always going to be twice x. So y is always going to be double what x is. So you can kind of just run through each one of these answer choices and see which one fits that. And then if there's multiple, you can actually just manually calculate what the area is going to be and then choose the bigger one. So using these, A must be out because x must be less than y. B looks very promising actually. X is exactly 1/2 of y, and also if you do 2x plus y, which is how you calculate the total fence used, you get exactly 1,000, which is right up there, so perfect. C is wrong because y is 3 times x. It must be 2 times x. And D is also wrong for the same reason. Y is 3 times x. I think B is our answer here because if you do, let's see, how much total fencing is used. We've got 2 values for x and 1 value of y. So our total fencing is going to be 2x plus y. Since x is 250 and y is 500, we can substitute those in. So 2 times 250 plus 500 equals 1,000. That's exactly what we said earlier. The fencing adds up to a perfect 1,000. So we know that B is our answer here. Question 6. Let f be a function whose derivative is given by this equation, f prime of x. The function f, so keep note, this is the original function f, not f prime. So the function f has what local maxima and what local minima. Cool. So this is a critical points question, so you always need to know what your critical points are if you want to find out what the maxima and minima are. So let's go ahead and find the critical points. To do that, we just set f's first derivative equal to 0 and then solve for x. They were really nice to us and literally just gave us f prime of x, so we didn't even need to calculate that. Just go ahead and plug it in. So 0 equals x minus 1 times x plus 3 times x minus 4. Now we need to solve for x, so we can go ahead and split this into three separate equations. So the first one's going to be x minus 1 equals 0, then we've got x plus 3 equals 0, and then finally x minus 4 equals 0. So we've got these three equations. We can just solve each of them independently to find all of our critical points. So the first one, x equals 1. Second one, x equals negative 3. And the third one, x equals 4. So it looks like we have three critical points, and we're probably also going to have three maxima or minima. Sometimes you have less than that. Sometimes critical points can be weird, but most of the time the number of critical points that you have is the same as the number of combined maxima and minima. So now that we have our critical points, let's set up our T-chart and figure out which is a maxima and which is a minima. So we've got our input, which is the values with some intermediary values. So we've got negative 3, 1, and 4. Some ones that can go in the middle. Let's see, we can do negative 4, 0 would be very easy. And let's do 2 and 5. That's a crappy 5. There we go. And then we've got our output. Since we are trying to find critical points, our output is going to be f prime of x. If we were to find inflection points, we'd probably want to use f double prime of x instead. So let's use f prime of x here, especially because we don't even have f of x. So we couldn't use that unless we took an integral. And also, we're already given our f prime of x. So let's just go ahead and use that. So we already know some of these values, namely our critical points, negative 3, 1, and 4, all equal 0. That's what we said back here. So don't have to find those. And now for the other ones, we do have to find. So f prime of negative 4, that equals, let's see, if we were to go up here, we've got three terms being multiplied together. And since we're only concerned with whether this is going to be positive or negative, we can just go ahead and find the sign of each of these three components and then go from there. So this is going to be three things multiplied together. The first one, negative 4 minus 1, that's going to be negative. Negative 4 plus 3, that's going to also be negative. And negative 4 minus 4 is also going to be negative. So this is going to end up being negative. So we're going to put a negative up there. Now f prime of 0, that's going to be same thing. We've got our three parts being multiplied. So 0 minus 1 is negative. 0 plus 3 is positive. 0 minus 4 is negative. That's going to end up being positive. Next one, f prime of 2. We have our three things. 2 minus 1 is positive. 2 plus 3 is positive. And 2 minus 4 is negative. This is going to end up being negative, so we'll put a negative up there. Finally, f prime of 5, that equals, let's see, 5 minus 1 is positive, 5 plus 3 is positive, and 5 minus 4 is also positive, so our answer is going to stay positive. So there we go. We have all of our intermediary points figured out. Now to just find out which of these are maxima and which of these are minima, we can look at all three of these critical points and their two surrounding or neighboring points and see what they mean. So let's look at the first one first, the critical point of x equals negative 3. So you'll see on its left, the slope is negative, and on the right, the slope is positive. So at that point, when x equals 3, the slope is going to be negative, and on the right, the slope is going to be positive. So because of that, it's going to form a local minima. So we know that negative 3 is a minima. So let's put min and max. Let's put negative 3 under the min. Now, next one is we have the critical point x equals 1. So this is the opposite case. So since we have positive 1, we have positive 1 up here, it's saying that the slope on the left is positive, but the slope on the right is negative. So because of that, we have a local maxima. So we'll put a 1 under the maxima. And our final critical point, x equals 4, it's the same thing as critical point x equals negative 3, where we have a negative slope on the left and a positive slope on the right. So that's what minimas look like. So we'll go ahead and put 4 under the minimums. Now, finally, we just have to figure out which answer choice fits that, and it looks like it's going to be E. There we go. It has a local maximum at x equals 1, that's that, and local minima at x equals -3 and 4, which is that. Cool. Question 7. On the open interval from 2 to 3 exclusive, the function f of x equals this is what? It's increasing in concave up, decreasing in concave down, increasing in concave down, or decreasing in concave up. It's probably not going to be E. They usually don't do that, so I'm just going to immediately cross it out. So, okay, so normally for these, increasing, decreasing, concave up, concave down problems, we need to find both of them. We need to find the intervals on which f of x is increasing and decreasing, and then we need to find the intervals in which f of x is concave up and concave down. So we need to find critical points and then inflection points. But fortunately, they already gave us the interval that it wants us to find this answer at. So what we can just do is first find f prime of x and f double prime of x, and then just plug in a value that's in this interval. So for example, 5/2, and then based off of that, if the outputs are positive or negative for both of them, we'll get our answer. So say if both of them are positive, that means it's going to be increasing and concave up. Our answer would be A. So let's just go ahead and do that by first finding those two derivatives. So f prime of x, that's going to be, let's see, derivative of x cubed, whoopsies, derivative of x cubed, that is 3x squared, minus, let's see, 6x squared, derivative of that, that's going to be negative 12x. Derivative of 9x is just 9, and the derivative of 30 is 0. So that is our first derivative, and then our second one, f double prime of x, let's see, that's going to be the derivative of 3x squared, so that's going to be 6x, minus the derivative of 12x, which is just 12, and then the derivative of 9 is just 0. So we have both of these derivatives now, so we can go ahead and do what I talked about earlier. Let's just go ahead and plug in 5/2 into both of them. And fortunately, we're only concerned with the sign of the output, whether it's positive or negative. So we don't have to do some of the legwork. We can just kind of approximate things as needed in order to get that sign. So let's start off with f prime of x, or f prime of 5/2, sorry. So this is going to be 3 times 5/2 squared minus 12 times 5/2 plus 9. This is going to equal 3 times, let's see, 5/2 squared is 25/4 minus 12 over 5/2. That's the same as 6 times 5 over 1, which is just 6 times 5, which is 30, plus 9. This equals, so this is going to be the hardest part of doing all this, but we can just still do it as 75 over 4. Minus 30 plus 9, that's just going to be minus 21. This equals, let's see, let's put that 21 in terms of just as a fraction, common denominator. So this is going to be 75 over 4 minus 84 over 4. This is going to be negative, since 75 minus 84 is negative. So we know that this is a negative, so it must be decreasing on the interval. So you know that A and C are wrong. Now we just have to do the same for f double prime of x. And what this will tell us is if it's concave up or concave down. So finding this, sorry, I keep moving my thing. F double prime of 5/2 equals 6 times 5/2 minus 12. This is a lot easier. This is 6 times 5/2 is the same as 3 times 5 over 1, and 3 times 5 is just 15 minus 12. That just equals 3, which is positive. So I know that it's concave up on the interval, so that means answer choice D is our correct one. Question 8. Find the point of inflection of the function ln x over x. All right, I don't know why they used point of inflection instead of just inflection point, but Anyways, that's what we're trying to find the inflection point of this function. And we know how to find those. We set the double derivative, or the second derivative, of f equal to 0, and then just solve for x. In this case, we have to do an additional step. This finds the x value, aka this, and then afterwards we just plug that into the original function to find our y value. So that's what we have to do. Now, first thing we have to do for this problem is finding that second derivative. So we have to do two derivatives onto this. So f prime of x, since this is a fraction, we should probably use the quotient rule, which is, I haven't done this in a while, a over b, that equals a prime b minus ab prime all over b squared. There we go, I still got it. So our a prime, that's the derivative of ln of x, that's just 1 over x, times b, which is x, minus a, which is ln of x, times b prime, that's the derivative of x, that's just 1. And then that's all divided by b squared, which is x squared. Normally, I don't recommend simplifying your derivatives, but since we have to do another derivative after this, it would help to simplify this just because we have more work to do on top of it. So let's see, this can be put together. It's just x over x, which is just 1. So this is going to be 1 minus ln of x. So 1 minus ln of x all over x squared is f prime of x. Now f double prime of x, that's going to be its second derivative. Looks like we can basically do the same thing. We've got our a and our b, so we can go ahead and use the quotient rule again, where our a is now 1 over, or 1 minus ln of x, and our b is x squared. So let's get started. We have our a prime, which is the derivative of 1 minus ln of x. That's just going to be negative 1 over x, times b, which is x squared, minus a, which is 1 minus ln of x, times b prime, that's the derivative of x squared, which is 2x. This is all divided by b squared, which is x squared squared, which is x to the 4th. Cool, so we have f double prime of x equals that. Now we can just go ahead and set it equal to 0 and see what we get. So go ahead and set this equal to 0. All right, let's make this easier. Let's keep f prime, double prime of x there, and let's go ahead and simplify this right now. So negative 1 over x times x squared is just negative x. This is minus 1 minus ln x times 2x. So this is going to be minus 2x plus 2x ln x all over x to the 4th. So we have this now. All of these terms have an x in it, so we can go ahead and remove all of those. So this is now negative 1 minus 2 minus 2 ln x all over x cubed. Now plugging in, we're not plugging in anything. We're solving for x. So let's see, 0 now equals negative 1 minus 2 is negative 3 plus 2 ln x all over x cubed. This looks difficult. Oh, actually, it's not very difficult. So we have a numerator and a denominator, and the only way for a fraction to be equal to 0 is if the numerator equals 0. So you basically can just forget about the denominator. So we have negative 3 plus 2 ln x equals 0 now. So we can add 3 on both sides to get, put it up here, so 3 equals 2 times ln of x. Divide by 2 on both sides, we get 3 halves equals ln of x. And then we can raise both sides to the power, we can treat all of it as an exponent with a base of e. This will get rid of the e to the ln of x, and we're just left with x equals e to the 3 halves. So it looks like our answer is going to be b, and we can double check our work by plugging that into the original function, into f of x. So let's go ahead and do that. Let's do ln of e to the 3 halves all over e to the 3 halves. This is equal to, ln of e to the 3 halves is just equal to 3 halves, and this is all over e to the 3 halves. So that is exactly what we're looking for, because this 3 halves just becomes 3 over 2, which is the y value of answer choice B. So we know we have our right answer. Question 9. The top and bottom margins of a poster are each 1 inch. So these margins here are both 1 inch. And the side margins are each 2 inches. So both of these two margins are 2 inches. So this is 1 inch here, and these are 2 inches there. If the area of printed material on the poster is fixed at 32 square inches, so that's going to be this inside area here is always going to be 32 square inches. Find the smallest possible area of the entire poster. So find the smallest possible area of the entire thing. All right, so this is a minimizing cost related rates problem. First thing we do is try to figure out what formula we're going to use that relates a lot of these pieces of information together. In this case, that's probably going to be the hardest part of this entire problem, just figuring out what formula we need to create in order to make all this come together. We can probably start by just writing down what the area of the printed material is, since we're given that, it's 32. And then from that, we can figure out what formula we can use for the entire area of the entire poster. So the inside area, that's 32, and we can just define two random variables for the width and the height. Maybe we can do W and H. So we have, let's call the inside area A sub 1 equals width times height. So A sub 1 equals width times height, which also happens to equal 32. It's always 32 for that area of the inside printed material. And now for the area of the entire thing, let's call it A sub 2. That's going to be, we can just basically leech off of these definitions of width and height and then incorporate those margins that we said earlier. So for the width, that's just going to be the width plus those two margins. So since we have two margins that are each 2 inches long, the width of the complete area is going to be width plus 4 inches. And now for the height, it's kind of the same thing. We just have to add those two margins in. It's two margins again, but each are only 1 inch tall. So this is going to be the height plus an extra 2 inches to calculate this outside area. So there we go. We have our total area figured out. This is really close to the formula that we're going to take the derivative of, but we have two variables here, and that's not a good thing. We always only want one variable when we take these derivatives. So what we can do is just take this definition that we already had for the inside material and put it in a, work with it and make it so that it's in terms of just one variable. So for example, we can divide both sides by W to get H equals 32 over W. And now since we have H equals, we know that that equals 32 over W, we can go ahead and substitute that in for the H down there. So we can replace this H with 32 over W. And now, for this formula, we only have one variable. We only have W in there. So it'll be really easy to take its derivative. So doing that, actually, let's not find the derivative yet. Let's make this easier on the eyes, easier to take the derivative of. Let's go ahead and FOIL this so that we have a bunch of just added terms there. I mean, it's really easy to find the derivative. So W times 32 over W is just 32. W times 2 is 2W. 4 times 32 over W is 128 over W. And 4 times 2 is just 8. And since we have two constants here, let's go ahead and put them together. Let's combine 32 and 8 to make 40. Not 48, sorry, just 40. So there we go. We have that all foiled out now, and now it should be easier to take its derivative. So let's go ahead and do that. So derivative of 40 is just 0. Derivatives of constants are just 0. Derivative of 2W is 2. And the derivative of 128 over W. So 128 over W is just the same as 128 times W to the power of negative 1. And when we write it like that, it's clear we can just do the power rule. Bring negative 1 out front, so this becomes minus 128. And now this is W to the negative 1. When you subtract 1 in the coefficient, that becomes W to the negative 2 power. And that's the same as 128 over W squared. So the derivative of 128 over w is negative 128 over w squared. And now this is our full derivative. Now to find the value at which w should be to minimize this area, we set it equal to 0. It's kind of just like finding critical points where you take the derivative and then set it equal to 0. So we do that and solve for w, and that will be the value of w that will minimize this area. So we can subtract 2 from both sides to get negative 2 equals 128 over w squared, or negative 128 over w squared. We can flip all these signs, multiply by negative 1 to make everything positive. Now it looks like we can multiply both sides by w squared, so we get 2 times w squared equals 128. We can divide both sides by 2, so we get w squared equals 64. And then square root both sides, we get w equals plus and minus 8. I wrote plus and minus here because technically those are two solutions for what w can equal, but does width being negative 8 make sense? Width should always be positive, so we can basically just forget about the negative term and realize that width must be 8 inches. So going back to the original problem, this width here must be 8. This length of the inside printed material must be 8 inches long. And based off of that, we can figure out the total area of the poster using our definition of the total area of the poster. So plugging in 8 for all those w's, we get 40 plus 2 times 8 plus 128 over 8. And simplifying this, we get 40 plus 16 plus 128 divided by 8 is 16. Yes, 16. So 40 plus 16 plus 16. And then adding these together, this will be 40 plus 32, which is 72. Answer choice A. Question 10. Consider the function f of x equals x to the power of 2/3 restricted to the domain from -1 to 1 inclusive. Which of the following statements are false? So before we hop into these 5 statements and figuring out which one is false, it becomes a lot easier to solve them if you're able to visualize either in your mind or on your paper what x to the power of 2/3 looks like. So since this is just a polynomial, which means it's x to the power of some constant, and this polynomial, since that power is between 0 and 1, it's sort of a decaying polynomial. So it looks something like this, where it starts off at the origin. So we've got our axes here. Whoops, that's a not straight line. Got our axes there, and it sort of goes up for a little bit, but keeps decaying and tapering off more and more, but it never quite declines. It's always increasing. So as x approaches infinity, the output also approaches infinity, but it does sort of decay and plateau like that. So that's what that looks like. And so this sort of looks like the graph of the square root of x. It looks really similar to that, but this is actually a little bit different because it's not x to the power of a half, it's x to the power of 2 over 3. And since that's not the same, we know that it's also going to have the same effect on the other side, because you can rewrite this as the cubed root of x squared. And whenever you plug in negative values into this x squared in the middle is going to make whatever you put in there positive. So it doesn't matter what you put in there, it's always going to work out even if you x is a negative number. So we do have this other half to worry about, but it's just mirrored like that. As x approaches negative infinity, this also approaches positive infinity. So we've got what this graph looks like, and now using this, it becomes easier to figure out which one of these 5 statements is false. So let me switch to red, and we'll start working through these. So statement A, on the domain from -1 to 1, f attains an absolute minimum value. So let's make our domain here from -1 to 1. Does f hit its minimum value here? Yes, it does. It hits it right at the origin. It's defined at x equals 0. In fact, if you do f of 0, it's just going to be 0. That's the minimum value, so it's in the domain, so you know that A is true, but it's not what we're looking for. We're looking for the one that's false, so it's wrong. Now, B, x equals 0 is a critical number for f. That is also true. It's asking about the same thing. So since we have our minimum value at x equals 0, it means that x equals 0 must be a critical point, a critical number. So B is true, so it's wrong. Now statement C, f of x is less than or equal to 1 for every value between -1 and 1. And that is also true because if you plug in, if you do f of -1 and f of 1, aka what these are going to be right here, those are going to equal 1 for both of them. So both of these are just 1. And you'll see that every value underneath this is also it's going to be less than that or equal to it right at those points. So because of that, f of x is less than or equal to 1 on every x value in that domain. So C is true, so it's wrong. Now, moving on to statement D, after I clean up a little bit. There we go. Statement D, there exists a value C between 0 and 1 where f prime of C equals 1. So if we have our value C that's between 0 and 1, is there a value where f prime of C equals 1? And yes, there is. So this is just the mean value theorem. This point here is 0, 0, and this point up here is 1, 1. So we know that the slope connecting both of those 2 points, if we do our little formula, is just going to be 1 minus 0 over 1 minus 0, which just equals 1. And the mean value theorem says, hey, if f of x is continuous and differentiable for all of these values, which it is, then there must be some value c where that slope equals 1. And that's exactly what D is saying. There exists a c between 0 and 1 where f prime of c equals 1. So D is true, so it's false. So we know that our answer must be E, but let's see what it says and figure out that it is actually the false one. So since f of -1 equals f of 1, which is true, f of -1 is equal to f of 1, there exists a c between -1 and 1 where f prime of c equals 0. So this one is false because this is asking about Rolle's theorem. So Rolle's theorem says if you have 2 points on a graph that are the same, they have the same output, which is true here. Those are on the same x or y value there. There must be a value between there where the slope is flat. But that isn't true because Rolle's theorem necessitates the graph to be continuous and differentiable for every point. And there's one point where it's not differentiable. It's right at the origin, since it has kind of a what do you call it? Like I don't know what the formal term is, but it's kind of pointy like that. It has a point right there, and you can't take the derivative of that point. So because of that, Rolle's theorem is not satisfied, so you can't say that there is a value where the slope is flat, is 0. So because of that, E is false, so it's the right answer here. Question 11. An ideal gas at a fixed temperature satisfies the equation P times V equals C, where P is pressure, V is volume, and C is held constant at 7,200 joules. At a certain instant, this gas occupies a volume of 3 cubic meters, and the pressure is increasing at a rate of 2 Pascal per second. Find the rate of change of the volume at this instant. So this is a related rates problem, but it's made a bit easier because they already have provided us with the formula that we're going to be taking the derivative of. So let's go ahead and take its derivative. Let's do the derivative of PV equals C. So the derivative of P times V, that's going to necessitate the product rule. We have two things being multiplied together. That is A prime B plus AB prime. So let's write that out. A prime is the derivative of P, that is dP over dV, or dt, sorry. Next up is B, which is just V, plus A, which is just P, times B prime. That's the derivative of V, which is dV over dt. And this is all equal to the derivative of c, which is just dc over dt. So let's, first off, what are we trying to find? We're trying to find the rate of change of the volume at this instant. So we're trying to find the rate of change of the volume, so we know that eventually we're going to have to solve for dv over dt, the rate of change of the volume. And just to make sure that we have everything else here, let's run through all of the other variables and make sure we can, we're at least provided with them, or we can figure out what they should be. So dp over dt, that's the rate at which the pressure is changing, gives us that right here, changing at a rate of 2 Pascal per second. So let's actually start building this formula. Let's put 2 there. V, that is the volume at this instant. It also gives us that. At this instant, it's going to be 3 cubic meters. So let's put a 3 there. Now, plus P, that is the pressure at this instant. And it doesn't give us that. So that at first seems like a problem, because it is. We need to find out what P needs to be. But it actually does give us enough information in the problem. We can just go ahead and figure it out by ourselves. So if you read what it says, C is always going to be 7,200. And at this instant, V is going to be 3. So if we plug both of those back into our original equation, we get P times 3 equals 7,200. And dividing both sides by 3, you get P equals, oh boy, 2,400. There we go. So we just figured out P based off of the information in the problem. It must be 2,400 Pascal at this instant. Now dV over dt, that's what we're looking for, the rate at which the volume is changing. And now dC over dt, that's the rate at which the, what is C? I don't know what C stands for, but it's the rate at which C is changing. And since C is held constant, that means the rate is 0. It never changes, so the rate is always 0. So cool, we have our full formula now with only one variable, the one we're looking for, so we can just solve for it, and then that'll be our answer. So simplifying now, 2 times 3 is 6, plus 2,400 times dV over dt equals 0. Subtracting 6 from both sides, we get 2,400 dV over dt equals -6. Divide both sides by 2,400, we get dV over dt equals so 2,400 divided by 6 is 400, so -1 over 400. And then the unit is, I don't know what the unit is, but it's going to be this, which is answer choice C. Okay, it's cubic meters per second, which, oh, that makes sense because it's cubic meters per second for the rate. So cool, we found the right answer. Question 12, find the shape of the graph of y equals 3x to the fourth minus 8x cubed. Okay, what would help for this is usually the best way of identifying these graphs is based off of these critical points, these maxima and minima. And when we find those, it becomes easier to tell which graph is which. So let's find the critical points of this function here. So first, we need to take its derivative. We need to find y prime. So y prime equals derivative of 3x to the fourth is 12x cubed. We can do power rule for that. And same thing for -8x cubed. That's going to be minus 24x squared. So that's the derivative. And now setting equal to 0, we get this 24x squared. We can take an x squared out of both of these two terms. So we get 0 equals x squared times 12x minus 24. And we can go ahead and split this off into two separate equations now. So x squared equals 0 and 12x minus 24 equals 0. Now for the left one, x equals 0, and the right one looks like we can divide everything by 12 to get x minus 2 equals 0. And then add 2 on both sides, we get x equals 2. So cool, we have our two critical points, x equals 0 and x equals 2. And that is the maximum number of critical points that we're going to have. So we can instantly rule out answer choice D because it has 3 critical points. Excuse me. So we've got our 2 possible critical points here. So what we can do to find which one is which is we can just plug them into the original function. We can do f of 0 and we can do f of 2 and see what we get. So f of 0, that is going to be 0 minus 0, which is just 0. And f of 2, I mean, we're really just concerned with if it's going to be above or below 0, so if it's positive or negative. Plugging in 2 for this term is going to be a very large number. Well, actually, let's actually figure this out. So this is going to be 3 times 2 to the 4th minus 8 times 2 cubed. This is going to be 2 to the 4th is 16. 16 times 3 is 48 minus 8 times 2 cubed. So 2 cubed is 8, and 8 times 8 is 64. This is going to be negative 16 up there. Cool, so we found our f of 2, which is below 0, and it's also to the right of it. So that looks like it's going to match A. So if you look at A, it's kind of got a critical point right here. That critical point doesn't correspond to either a minima or a maxima, but those are indeed critical points. If you look at the graph of just x cubed, that looks like this. And 0 at the middle is its one and only critical point, but it's not either a maxima or a minima. So A up here, that is a critical point. That probably corresponds to this 0. And then the critical point down here must be this f of 2, this negative 16. And that checks out because A, it's to the right of it, which makes sense because 2 is bigger than 0. And it's below it, which checks out because negative 16 is less than 0. So both of those check out. I'm leaning to believe that A is our right answer. So I'm going to circle it.